This is fun. 1 plus 0.2x. Okay, one of these is supply and one of these is demand. Hey, Chica. All right. That was supply. Okay, so this was demand, and this was supply. And it wanted us to find consumer surplus, correct? We're already there, guys. Okay. Find consumer surplus under pure competition. Okay. So the first thing is we can either set these equal to each other and solve for x, or we can graph them. I vote for graphing. So I'm going to graph these suckers. I know I'm not going to need a lot of room on my graphing utility, which is not here. So that's cool. I have it on my phone. I'll just do it on my phone. No, I don't want to sign into your effing network.
Do you want my calculator?
Nah, I'm good. It's right here, see?
Oh, sweet.
Yeah, 12 divided by x plus 1. It's just as fast as the other one. And 1 plus 0.2x. So I'm going to graph these suckers. And what I get is something that looks like this. And something that looks like this.
And do you set it equal to each other, to demand and supply?
Yeah, so graphically, you would set them equal to each other, and that's this point right here. That's the point where they intersect. So how do I find that point? Well, I go to second calc, down to intersect, and then I make sure my cursor is near the point that I care about, and I hit enter 3 times, and it gives me the intersection of x equals 5, y equals 2. So that's x equals 5 and y equals 2. Well, that's my p sub e on the y-axis, and that's my x sub e on the x-axis. So now I have everything I need, right? I have my demand function, I have p sub e, and I have x sub e, and those are the 3 things I need to find consumer surplus. So here we go. Consumer surplus is the integral of demand, 12 over x plus 1, with respect to x minus p sub e times x sub e, so 2 times 5. Well, when I make this pretty, what integral are we finding? Oh, and I should be going from 0 to 5 on this, right? Because it's a definite integral. So which integral is this? 1, 2, 3, or 4?
1.
No.
Oh, it's 3.
Yes, it's number 4. Why is it number 4?
Because of the minus 1.
It's the -1 that gives it away, right? So we have something times a function to a power, and that power is a -1 automatically. This is number 4. So, what's my u? Yeah, u is x plus 1. What's my u prime? 1. What do we have? What do we want? So we have 12. We want 1. So if I kick the 12 out, will there be a 1 left over? Yeah, so let's do that. Let's just pop that right out of there. So I'm going to move this down a little bit. So I have 12 integral from 0 to 5. 1 times x plus 1 to the -1st with respect to x minus 10. Am I ready to integrate, guys? Great, what is it? 12? Natural log. X plus 1. We're doing that from 0 to 5, and then we subtract 10. Yeah. And I think you can take it from there. So, who asked for this one? Naomi, talk to me. Where'd you go off the rails? Hang on, Sal.
I feel like it was just, I got the integration part, it's just when I started plugging in all the numbers.
Oh, you want me to keep going?
No, it's like it didn't look right to me.
Oh, yeah. Just for giggles, I'll go ahead and finish it off for you. Sal, what was your question?
On my calculator, I didn't get that.
You didn't get that intersection? Huh. Can I take a look at what you have on your calculator? Plus you have 0.2 or 0.02. That's the difference. Let me double check that I wrote it out right. Yeah. So just move that decimal over and it should work for you. Groovy? Okay, so now we just say 12 natural log of 6 minus 12 natural log of 1 minus 10. Well, I can do part of this in my head. What's the natural log of 1 equal, guys? 0. So 12 times 0 is, wake up, 0. So now we just do 12 natural log of 6 minus 10, and that's our consumer surplus. What was the hardest part for you guys? If this is the first time you're seeing it, talk to me. What was the hardest part? Saeed?
Yeah, I was absent probably, but how did the natural log get into all of this? I get it till the integral?
No, it's because of the -1. Grab your tattoo.
Oh, I see.
Grab your tattoo and take a look at the integrals. The only one that can have a -1 on that exponent is integral number 4, and that's the natural log of u.
So when you have the natural log,
Mm-hmm.
the 12 ln x plus 1,
Yeah.
the x doesn't get a 1 plus 1 on it because the
No,
integral.
no. Yeah, the nature of the nature of the integral of natural log, u prime u to the -1 with respect to x, that equals the natural log of u
Okay.
plus k. Unless we're doing a definite integral, then it's the natural log of u from a to b.
Okay.
Yeah, so there's no +1 or anything in there. It's straight out of your tattoo, Maria. So
Yeah.
you're gonna wanna definitely
Look at it.
refer to that
Yeah.
sucker. If you're not comfortable with these functions and not comfortable with your integral patterns,
Mhm.
make sure to use your tattoo. That's what it's there for. It's there to support you. Yeah. Alrighty, so let's look at number 29. Everyone's so quiet this morning. Good morning. How you doing, Jesus? $29. Aha. Okay. If the supply function for a commodity is P equals 10e to the x over 3, so this is supply, 10, or P equals 10e to the x over 3. And what is the producer surplus when 15 units are sold? So find producer surplus. That's 7.
I wonder my win today.
Yeah, you might. When 15 units are sold. So let's take a look at the integral formula for producer surplus. Producer surplus is P sub E times X sub E minus the integral from 0 to X sub E of supply with respect to X. So what are we missing? This is a little squished. We're missing what? Yeah, P sub E. So supply P equals, that's a little prettier. Okay, we're missing X sub E. We're missing P sub E. This is our X sub E. We have 15 units. So how do we determine price when we have our X? Plug it in. Plug it in where? Plug it into the supply function for X, right? It's an X value, so we're gonna shove it in for the X value and just see what happens. So price at equilibrium is gonna be 10e to the 15 over 3, which is just 10e to the 5th, which is what number, guys? 1484.13. And since this is a price, that's in dollars. Okay, so great. We have everything we need. Are you guys ready? Let's plug this puppy in. So producer surplus is price at equilibrium, 1484.13 times quantity at equilibrium.
Getting close to that nine.
Getting so close. Times 15 minus 0 to 15. 10 e to the, I'm gonna go ahead and make this a 1/3 x on my exponent. By the way, which integral is this?
This is the second one.
It's not number 1.
Oh, the E, the third.
Yeah, it's number 3.
Number 3.
Why is it number 3?
Because of the E.
Because of the E. E is 3. E is 3, guys. So our formula for number 3 is, I can do this. Oh boy. U prime e to the u with respect to x becomes e to the u plus k, or e to the u from a to b. Okay. So what's our u? 1/3 x. What's our u prime? What do we have? 10. What do we want? 1/3. So what are we going to multiply and divide by?
3.
Yes, 3. Okay. What is 1484.13 times 15? Thank you, you guys. Awesome. Thank you, Griffin. All right, so minus 30. Don't worry, you guys. I'll let you sit with this for a second. And you can tell me what I did. Gesundheit. La la la.
How did you get the 30?
I was waiting for somebody to ask. All right, you guys.
30.
You see how?
I think I see it.
Talk to me.
You divided the 10 by 1/3. Or
I-
divided 1/3 by 10.
I multiplied and divided by 3, right?
Oh, right,
Right.
right.
So I
see
kept the
10.
one on the bottom and I kicked out the one on top because I
Yeah.
need a 1/3,
Yeah,
right?
Yeah.
So if I kicked out the one on top plus the
Mhm.
10, what's 10 times 3? 30. So there it is. Give me a thumb if you guys see it. Give me a shaker if you're kind of there. All right. All right. Okay. Where did I lose those of you that felt lost? Let me do that internal step. Minus integral 3 divided by 3 times, nope, not a 30, a 10. 10 e to the 1/3 x. So again, I need a 1/3. I'm gonna keep this one and I'm gonna kick those out. Better? Awesome.
Yeah.
Okay.
Can you
Huh.
multiply by 1/3 instead of 3/3?
Yes, you can, but if you multiply by 1/3, you must also divide by 1/3. And now you have a fraction on your denominator.
So it's like the donut?
To me, this is cleaner. Yeah, you would do the donut in that case. To me, this is cleaner, but whatever floats your boat. All I say is that I know I need a 3. I don't care if it's on the numerator or the denominator. I know I need a 3. So I'm just going to multiply and divide by 3 and circle the part that I need, right? We've been synthesizing these for a while. So now I know I don't have to keep the numerator. I can toss out the numerator if I want, keep the denominator. Multiplication and division are sisters. So pick your poison. Yes, you can multiply and divide by 1/3, but I think that gets a little snaky because you have a fraction over a fraction. But that's just me. All right, so now what's the integral? So we're at, I'm gonna erase this little half step here just to keep it clean. So now we're at the point of integration. So we have 22 to 61.95 minus 30 e to the 1/3 x. But I want to caution you guys, the thing that we're doing 0 to 15 from is everything inside these brackets, okay? That minus sign
Stays out.
is out. So we still have to do f of b minus f of a within these brackets. So your signs are going to be important here. And I'm gonna, who asked for this one? Ah, Nikki, where did you get lost working on this problem? We're at 10! Good morning!
It was like the 1/3.
It was the 1/3 becoming a 30? Yeah. So you're good now?
Yeah.
You can plug it in. Just watch your signs at this point, okay, guys? All right. Anything else? You guys happy? You ready to tackle something new today? So excited. It's the second to last lecture, you guys. And we are done with integration. Take a deep breath. You're like, I was just getting used to that. Now we're done with it. Just when you thought you were getting good. So, I want to talk to you guys about old-fashioned derivatives for a second. Old-fashioned derivatives. So here we have x versus y. This is the 2D derivatives that we've been doing all along, right? Here's some function. And if you plug a specific x in, you get a specific slope out. And if you plug a specific x in, you get a specific slope out, right? Because that's what we do when we mess with derivatives. Plug an x in, get a slope out. Well, if we plug an x into the function, what do we get out?
A y.
A y. So x is our input variable, or our independent variable, but people seem to get lost with that word, so I'm going to use an input. And this is our output in 2D. Well, remember what we did with slopes. If x goes over by how much? It's always over by 1, right? It's always over by 1. So if x went over by 1, how much are we expecting a change in y? We're going to move this to 3D now, okay? We're going to move this into 3D, and we're going to talk about what's called a partial derivative. So today, I want you guys to imagine, I'm going to stand here in the corner, and I want you, I can't decide what's the best corner for me. Yeah, I'll just stand here. I'm going to imagine that this corner right here in the floor is my origin. And this is my x-axis going out here along this line of the floor, x-axis. And my y-axis is the line along this floor right here. And my z-axis is here, okay?
Is
So
on the
this
top.
is- What?
Z-axis, you said?
Z-axis goes straight up from the
Okay.
floor. So that if I were to draw this on the board, I have my y-axis out here,
Mhm.
my x-axis coming out like this, and my z-axis going straight up, okay? So this is this guy right here, y is straight out like that, z is straight up. So far, so groovy.
Yes.
Okay.
Is all this on a handout?
Yeah, sort of. I get more into the math in the handout and less into the concept, but it's okay. I'll talk to you guys about it. So before we were working in 2D just with lines. Well, in 3D we work with surfaces. We don't work with lines. So I'm going to talk to you guys about surfaces here for a second. But before I do, let's talk about input variables and output variables. X and Y are now our input variables. And Z is our output. So before, we could say that Y is a function of X. But now, we're saying z is a function of x and y. So far, so good? All right.
Is this like a new chapter or
Oh, yeah.
so?
This is chapter 14.
14.1.
2.
Did we skip 14.1?
Yes. 14.2 is partial derivatives. And everyone's wondering why the hell I have a trash can up here. And I say to that, it is not trash, it is recycling. So here's a surface. I just want you to look at this surface right here, the very top surface. Shut up, Saeed. Saw you laughing back there. And this is sitting somewhere in this grid, okay? And if I choose a point, let's say the dead center of this this recycle scenario, this consists of some x out from the origin, some y out from the origin, and some z up from the origin. So far, so good?
Yeah.
So just like a point on 2D that consists of an x and a y, this point consists of an x, a y, and a z. You guys with me so far? Okay. So
Because we're
if-
talking about surfaces.
yeah, I'm talking about surfaces. So this point on this surface in space consists of an x and a y and a z. And so does this one, and so does this one, and so does this one, and so does this one. All of them. It's an infinite number of points on a surface. Well, now, where is my smack stick? It's so easy to see with the smack stick. There have been smack sticks in this thing all semester long. Oh, there's one. Goody. All hiding. Ha! I can do them at the same time. Hot diggity. This makes me happy. Okay, so I'm back on my surface. So I want to look to see if the slope in the y direction is changing. So my y direction's over here, right? So if I go over 1 in the y direction and I hold x constant, guys, is z going to be going up or down? Sorry, this is approximately the y direction. Is that moving up or down slightly? Down. Okay, so if I go over 1 in the y direction and hold x constant, z is going to go down, right? What if I hold y constant and I vary x? Is z going to go up or down? Down. Is this juicy? It's probably juicy.
How much material is in
So much. That's why I wash my hands. Okay, so now, damn it, let's look at this surface. What's happening in the y direction if I vary y and hold x constant? Nothing, right? We've got a slope of 0 approximately, yes? What about in the x direction on the same point? Z is gonna go up. So you guys see how you can have 2 different slopes at the same point in 2 different directions. Everyone okay with this? Caitlin, come visit me. Now, let's apply this to math in a conceptual sense first. How many of you are bakers? Okay, that's more than the other class. The other class was like, no raising hands. That was really interesting. I cried a little. Okay, so how many of you have baked a cake out of a box before? Let's start simple. Okay, a lot more hands go up. What's involved? We need 3 eggs, basically a half a cup of oil and a cup of water, right? That's essentially what we need. So those are the variables that can go into baking a cake, right? And if we change the number of eggs, will that change the consistency of the cake? If we change the amount of oil, will that change the consistency of the cake? Okay, if we change the amount of water, will that change the consistency of the cake? If we change all 3 at once, can we tell which one affected the consistency of the cake? No, and that's why we do partial derivatives. We isolate a single variable and we change them one at a time so that we can see how that one thing affects the overall picture, right? So far, so good. So that concept is solid, yes?
Yeah.
Okay, let's do it again with a different kind of demonstration. How many legs does it take for me to walk like this? Don't overthink it. 2. If I hold one constant and I vary the other, I get this motion. Okay, hold that motion in your head. If I hold the other leg constant and I vary the other leg, I get this motion. Are those two motions the same?
No.
No, they're not. So I could do a partial derivative in 2 different directions and get 2 different answers off of the same motion. You guys with me? Okay. All right. So far, so groovy? All right.
You mean because you could have gone backwards too?
Well, because I'm holding one variable constant, I need 2 variables to walk, right? If I'm holding one variable constant and I keep moving the other variable, I'm gonna get a certain motion out of it. I'm gonna get some result. And if I hold this variable constant and move the other one, I'm gonna get a different result.
You said you would get 2 answers out of one motion.
Yes,
Is that
I-
because you can like go
this
back?
is my function, right? I'm walking. And now if I take a partial derivative, I can hold one of my variables constant and move the other one and get some slope as a result. And I can get some slope as a result of my other foot moving and the other foot staying still. Okay, now, let's think about cost for a second. What does it take to build things? Money. Okay, what do we spend that money on?
Labor and material.
Labor and materials, those are the big 2. So let's think deep dive. No, not deep dive. Let's go shallow dive right now. We're gonna build a toy made out of wood. Like old style Amish toy, all wood. What are the things we need to build that toy?
Tools,
Tools,
wood,
wood,
and skill.
and people, right? People to run those tools. Yeah? Okay, so all of those things take money, right? That's 3 variables right there. Just right there. And that's a simple, like, manufacturing problem. Materials, labor, and tools that go along to build the materials. Manufacturing equipment. So far, so groovy. So if I hold all the others constant and I vary one, I can see how that one thing affects my overall cost. Say that my materials cost has gone up because my suppliers' prices have increased, and I want to see how that affects my overall cost. I can do a partial derivative of my cost function with respect to materials and see how that thing overall affects my cost. You guys with me so far? Yes, kind of no. Give me a shaker if you're not quite there. Thumb up if you're good. Thumb down if you're like, yeah, yes. Okay. All right.
I think when we
Really?
see an example, it might stick in.
It's easier than you guys think it is. So the math of this, don't stress about it too much. La 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 la. Let's look at a simple example to start with. Why do you know Z? Jesus, I can't hold on to the thing today. Z equals 3x to the 4th y squared minus 10x plus 15y minus 8. Some function. And I want you guys to find, you're gonna love this, partial of z with respect to x and the partial of z with respect to y. And you're like, what's that symbol? I can hear it already. What is that symbol? Well, before we had the derivative of y with respect to x. This was a command. Take the full derivative of y with respect to x. Nice, tall, strong b, right? This is a partial derivative. So it's not a full d. It's kind of a, okay.
It's a
Yeah.
kind of a Greek symbol.
Ah, I don't even know what it is. I just think of it as the partial symbol. Yeah. This is the partial of partial of z with respect to x. So let me talk you guys through this to start with. X is gonna be the variable. And if x is our variable, we're gonna hold everything else constant. Yeah. I'm watching you guys. My eyes on you. If x is our variable, what's constant? Everything else, not z. Z is our output, still variable. But everything else in the function itself is constant. So I'm gonna underline all of my x's in the same color. So those are the terms that contain the variable. Every other term that doesn't contain the variable is a constant. And what do we do to constants that are by themselves when we take derivatives?
It
We kill them,
disappears.
killer. Yeah, they disappear. So let's do this derivative one step at a time. Okay, so 3y squared is now our constant. So it's gonna come along for the right. What's the derivative of x to the fourth? 4x cubed, and we still have that 3y squared coming along. Is everyone okay with that? What's the derivative of negative 10x with respect to x?
10.
What's the derivative of 15y with
15.
respect to x?
15y.
Just 15. Why not 15?
Does it contain a variable?
Why?
No.
Oh, yes, I
Your
see.
variable is x.
Is only x.
Doesn't contain a variable, it's
So it
constant.
falls off.
You kill it, killer.
Kill it.
And that 8 is also to 0.
Yeah.
So if I were to simplify this, I would say it's 12x cubed y squared minus 10.
I see it. Yeah.
Okay? Is everyone okay with this? Caitlin, talk to me. I can see your brain working.
I don't understand why you didn't just do 4 times